All right, good morning. Just going to pick out problems from packet 3, and feel free to ask any questions if you have any. All right, so let's start with number 2. And I'll just try to do a problem from every category, or as much as I can. All right, it's our first step. Good, right. So go ahead and substitute that x. Ignore the one-sided limit. We're not going to don't get distracted by that. There's no decimals, at least not yet, right? So plug that negative 11 in. So I get root 8 minus root 8 over negative 11 plus 11, so 0 over 0. Indeterminate form. So we have some options here. So indeterminate form. We know that there's a hole in the graph, but the limit is going to exist. We just haven't found the answer yet. Okay, you have two options. If you saw this on the exam, you can choose either option to do. You can either apply conjugate method, or you can use L'Hopital's rule. Either way works. I'll go through both methods, and you can decide on your own which one you want to potentially use if you come across this problem. So I'll do the conjugate method first. Now, the purpose of this method is to try and get the numerator cleaned up to a place that will match that denominator. We know that this is the denominator that we're trying to get a matching pair in the numerator to show up. Not always positive, just always the opposite sign. Yeah, always opposite sign. And make sure that your numerator and denominator are the exact copy, exact same. Yeah. Okay, so now we're going to FOIL, but when we FOIL, we're only going to take care of the numerator. The denominator, we're going to leave that alone. It's already displaying what we want to cancel out. All right, so x plus 19 minus 8 cleans up nicely. We get x plus 11. And this x plus 11 ends up reducing with the denominator. We're left with a 1 in the numerator. The whole has been accounted for. It's been taken care of. So what's our final step? Okay. Oh yeah, so I took a shortcut here. I just did 19 minus 8.
Oh, okay.
And I just, rather than writing everything again, I just put that above.
Okay.
Cancel it out. Okay, and then our final step, we make that final substitution, right? Okay, that's option 1. We have a second option, which is L'Hopital's rule, because we have 0 over 0. We have this option available to us. Good morning, Vivon. How are you?
Good morning, Mr. Yang. I'm good. Thank you.
Good. So because we have 0 over 0, we know we can find the derivative of the numerator and denominator separately, reevaluate, and that should take us to the same answer. But initially, I'm just going to rewrite the numerator to get it ready for my derivative process. I'm thinking chain rule, but I want to get that radical with the variable to be rewritten. Okay, so same thing. We've already established a 0 over 0 before we jumped into these steps. Okay, so now L'Hopital's rule. Power rule, or chain rule here. Outside derivative times inside derivative. A little bit of a chain rule here. Inside portion is my x plus 19. Okay, outside derivative, 1/2 parentheses to the negative 1/2 times the inside derivative times 1. Okay, so that's the result. This is the result of my derivative of this first term, minus the root 8 goes away to 0. And then we also find the derivative of the denominator. X becomes 1, 11 becomes 0. So really, when we do our substitution here, we're just going to be taking care of that numerator. There's nothing left in the denominator, just a 1. So let's see what happens when we reevaluate after taking the derivative, applying L'Hopital's rule here. (1/2), 8 to the negative 1/2. Same thing as bringing that 8 back down to the denominator, make it share the same space, and then converting it back to a radical. So either process works. Okay, questions? Let's skip to number 12 over the 12. Number 12 says, find the point on the graph of y equals square root of x where the tangent to the graph has the same slope as the line through 1, 1, and 9, 3. So really, if we kind of read between the lines here, this is really talking about mean value theorem, because mean value theorem is if you look at the wording here, it says the tangent to the graph. So tangent comes from f prime. In other words, kind of a derivative related word there. The same slope between the endpoints. So this is the slope between the endpoints. And then a visual representation is this here. Right? Whatever the graph looks like, the slope between the endpoints, we want that to match the slope at a specific point. So without saying it, this problem is asking us to apply mean value theorem. So we're just going to apply mean value theorem, look for ordered pairs. All right, we want to take care of this piece of the puzzle first. So first we want to find points or find slope. We have ordered pairs given to us, right? We have 1, 1 and 3, 9. I'm sorry. 9, 3, my bad. I got these mixed up here. Going from 1 to 9. Okay, so the slope part of it, f of b minus f of a over b minus a, that's the change in y over the change in x. Okay, so I have that portion figured out. This is my now we're moving on to the f prime side of things. We want to ask the derivative to tell us a location where a specific slope is going to occur. So we're going to set our function, get it ready for the derivative. Y prime. That's my f prime piece of things. So I have my slope information, I have my derivative information, and now I'm just going to set these equal to each other and find the location where this particular slope is going to exist on this curve. Cross multiply. Square both sides. We only have one solution, and this should be a guarantee. This should fall nicely between the endpoints, and it does. It falls between 1 and 9, so our C value is 4. In the end, it's asking for the point, so all this we know that's the x value. It's asking for the point, so we can just put that 4 back into the original function. So the point is 4, and then put 4 in for the x, square root of 4 is 2. So that's going to be our answer here, answer choice D. Oh, back into the original equation. So plug 4 into f of x. So since y equals square root of x,
like the conditions are that it has to be continuous and differentiable. But this is not a polynomial. So how do we determine that?
Right. So you're right. It's not a polynomial. As long as it's continuous within our interval, we're okay. So there's a restriction with square root of x, and it's the fact that the domain has to exist from 0 to infinity. It's not a polynomial, but there's no denominator, which means that as long as my graph exists within the domain, we're not going to have any issues of sharp turns or any vertical asymptotes. So as long as our interval falls nicely between our domain, we know we're safe. But yeah, technically, we should have checked continuity and differentiability. Yeah. But for our purposes, the only time you really have to be worried is if you see a variable in the denominator. If you see like y is equal to 3x over x minus 4, then you'll be more concerned because you know that there is a potential break. All right. Let's do an implicit one here, number 14. Again, we're working off of packet 3. All right, consider the curve. The slope of the tangent is, so we're just asking for the slope here. So we just want to find the derivative really first. Basically, it's saying find the slope of the curve at 2, 1. So I see a couple of things. You want to list anything out? Can you see derivative-wise? Okay. Good. All right. Product rule because of the two variables here that are being multiplied. Implicit because we see kind of y is kind of mixed into the equation. We know that we're expecting some dy dx's along the way. I see 2 y's, which means that when I get to my derivative line, I should be expecting 2 dy dx's. So I'm just going to go down the line here. Take the derivative one piece at a time. X becomes 1. X times y. I'm going to set this up here. Product rule. Okay. So x becomes 1. G function stays. Back to f. And then g prime, which is asking for y's derivative. Y's derivative is 1. And then we always attach dy dx for any y variables once we are asking for its derivative. Okay, continue moving. 2y squared. We find its derivative going through power rule, which is 4y. And then we attach dy dx. Careful with the 6. I think a lot of students want to think that the 6 is going to stay, but that 6 is also getting impacted. So it's a constant. Constant goes to 0. Make sure we don't leave that as a 6. Okay, let's get dy dx by itself. Factor the dy dx out. Divide both sides by x plus 4y. And this is the notation to indicate that I'm going to be plugging order pair into the derivative, but because I have x and y, I'm both plugging both in. This is usually the notation that you see to indicate that I'm going to be plugging both the x and y values into my derivative. This is a little bit more involved than other derivatives because y's are in my equation. Let's see, I missed something here. Oh, the 1. I lost track of the 1. Okay, let's see. -1 here. Yeah, so the 1 should have moved over along with the y. So when it moves over, it becomes -y minus 1. Divide that over. So -1 minus 1 should be -2 over 6, which is -1. That's our slope. Questions? Let me extend this problem one step further. Let's say there was a part 2 to this that was asking for the tangent line equation. Then all we do is we take the slope. The slope process was a little bit more involved because it's implicit, but it's the same thing as other slopes. So we just take our slope, we take our ordered pair, and then we just do point slope. Let's do a particle motion problem. This is number 19. So 19 reads that a particle moves along the x-axis so that its position is given by x of t. I'm going to extend this problem a little bit as well. First part, let's find the particle at rest. And then next, let's find interval particle moving right. So let me just talk about our strategy to going about these problems here. So finding particle at rest, we're starting with position, right? So we just have to really just to set the velocity equal to 0. And then whatever the result of that is where my particle is at rest. And the interval moving right, we're just going to create a velocity sign line and pick off information off of that. Okay, so there's our strategy. We're going to work off of that. So to find velocity, I got to get to the derivative. To get to the derivative, I have to use what? Quotient rule, yeah. Variables, numerator, denominator, there's no way around it. If one of these sides was not a variable, then I would move things around and just try to avoid quotient rule. Right? Continue cleaning up, I get 4 minus t squared. Okay, so there's my derivative. Or there's my velocity function. Okay, so now it's asking for where particle is at rest. And when we set the velocity equal to 0, there's a very specific location that we look. Where is that? Where do we find, how do we set velocity equal to 0? Do we set both equal to 0? Okay, just the numerator. Okay, we're just going to set the numerator equal to 0. Because if we set the denominator equal to 0, then we're asking when the velocity is undefined, right? And that's not what we want. We want when the velocity is 0, so just the numerator. Yeah. Sure. So this is the result of quotient rule here, and I'm just combining like terms here. So 1t squared minus 2t squared is going to be negative 1t squared. And I just made that 4 minus t squared. All right, so just the numerator equal to 0. Oh, there's an additional restriction here. It says time is t greater than or equal to 0. So they're giving us restriction that we're only dealing with numbers 0 and numbers to the right of 0. So I get t is equal to plus or minus 2. But negative 2 is outside of our interval. So we can say particle is at rest when t is equal to 2. Velocity is 0. Okay, so that's part A, or part 1. Part 2, we want to know interval moving right. So we're going to create our velocity sign line. I know I can have 0 as my starting point because they're giving us that restriction. Again, here's my velocity function. Choose values in each interval to plug in. I'll plug 1. 4 minus 1 that's positive. Positive over positive. So positive is moving right. Let's test 3. 4 minus 3 squared, that's 4 minus 9, that's negative over a positive. I know the denominator is always positive because everything is squared. Okay, so we can say particle moving right. There's something a little tricky here. What's the interval, you think? It's greater than 0, but then 0 to 2. But there's something else. Do you see it? I mean, this is the interval. But there's something we got to test, and it's the fact that t is greater than or equal to 0. So what that means is that 0 didn't show up when particle is at rest. So it's possible that this particle is already moving at 0. So we need to test what's happening at 0. If I put 0 into the velocity function, I'm getting 4 minus 0, which is 4 over 4 squared. That's positive. So we just have to include 0 in our interval. So either you write it that way, or you can say moving right with a bracket, because velocity is positive. Yeah, so it's just a subtle thing here with the bracket instead of a parentheses. Okay, related rates. This is number 25. Okay, triangle shown. We know that when we're dealing with theta, we're just going to be working with trying to decide on the trig function. So everything's already labeled for us. We just have to figure out whether to use sine, cosine, or tangent. What do you think? Right. Between sine, cosine, tangent, which is going to hit all three? Sine, yeah. Okay, go ahead and find the derivative. Sine theta becomes cosine theta. d theta dt. That's the unique thing about related rates, is that we're always going to have those d over dt's that show up. X over 5 is the same thing as 1/5 x. And just think of it as power rule, easy power rule problem here. 1/5 x becomes 1/5 dx dt. All right, let's see what the problem tells us. Theta is increasing at a constant rate of 3 radians per second. So theta increasing, we know that is time related. We see per minute, we know that's time related, so that's d theta dt. Increasing, so positive 3. X increasing, we want to know at what rate is x increasing. So we're looking for, we're looking for dx dt. That's our end goal. When x equals 3 units. So if we look, we know we're looking for dx dt. That's our end goal. So we know we have that showing up in our equation. D theta dt, we have that accounted for. But the one missing piece that we still have to resolve is this cosine theta. So the easiest way to get to that is I'm going to create a second triangle and see if I can populate the triangle with values on all 3 sides. And then I can figure out that ratio for this triangle. Okay, x is 3. Hypotenuse is 5. Pythagorean theorem. I know that my missing side is 4. So now we can figure out what cosine of theta is, which is so that is going to go in place. So I think we have everything accounted for, right? We have everything that we need to solve for our missing variable. So let's just plug in. Okay, 4/5 replaces cosine theta. D theta dt gets replaced with 3. And then we're just going to solve for dx dt. Okay, so really the only thing out of place here is that 5, right? I can divide by 1/5, which is the same thing as multiplying by the reciprocal. So I'm just going to put all this together and figure out what dx dt is. Fives cancel out, we just get 12. What is it? Feet per minute. No. 35, reading a derivative graph. So f prime is drawn. Which of the following is true? Why don't we just gather a bunch of information, just for practice purposes here, about this derivative graph in terms of, let's create a velocity, let's try create a derivative sign line and a second derivative sign line, and then we can have everything in front of us in terms of increase, decrease, relative max, relative min, concave up, concave down, POI. So I'm going to resketch the graph here. Okay, here's my f prime graph. I'm just going to gather a bunch of information from my f prime graph in terms of things I want to find out about my function. So I like to start off by labeling. Anything above is going to represent positive slope. Anything below is going to represent negative slope of the original function. Anything on the x-axis is slope 0. So here's my slope sign line. I'm going from -3 to 4. Start off with critical points. -2, 1, and 3. Okay, we pick out the locations where the graph exists. We don't want to look at how the graph is rising or falling. That's something else that we're going to get to. Right now, let's just look at where these slope values are. Above the x-axis represents positive slope. Below is negative slope. So we see that all this first interval here from -3 to -2 is above the x-axis. So that's going to translate to positive slope. Below the x-axis, that's going to translate to negative slope. From 1 to 3, still negative slope. And then from 3 to 4, then it starts to peak above the x-axis, so positive slope. So these arrows gives us a much better idea of how the graph actually looks, right? We expect a relative max at -2, a relative min at 3. Let me just write those. And then you can obviously tell where the increase and decrease are. That's pretty straightforward. But I just want to just make a note, max and mins. We can also gather information about concavity, right? Second derivative sign line, also extending from endpoint to endpoint. But now, how do we find points of inflection to place onto our sign line? Where do we look? Yeah. So points of inflection are going to be the peaks and valleys, the max and mins. This is not how point of inflection looks on the original graph, but this is how points of inflection, this is how we can spot the points of inflection that's going to exist on the original graph. So -1, 1, and 2. And now to determine concave up, concave down of the original graph, we look at the slope. Okay, don't look at the curvature, right? This again is not the original graph. So the way we find information about the original graph is a little bit different. Look at the slope. Negative slope translates to This tells us that the slope is becoming more negative, which in actuality is going to indicate where my graph of f of x is concave down. Positive slope. So notice that all this is still in the negative region, but the slope is becoming more positive, and the curvature is going to resemble that of concave up. Negative slope, concave down, and positive slope, concave up. Okay, so I think we probably have more than enough information to answer our question here. So let's see what the question says. It's saying f is increasing on the interval from 2 to 4, and we see that's not true, right? Portions of it is, but not all the way from 2 to 4, so we know that this option is out. Relative minimum at negative 2, we don't see that either, right? Obviously not a relative min, that's relative max. And then the graph has an inflection point at x equals 1. That we can say is true. Right, so the answer choice is just 3. 3 only. I do want to extend the problem a little bit. What if we wanted to match this derivative graph with what the original graph looks like? So what we can do is, let's use this information and sketch our own version of the graph. And at least you have something to match with the answer choice. Your graph may not be in the exact same location, but it should have the same shape, and that's all you need, right? You just want to know what the shape of the graph is, and then that'll make your matching a little easier. So here's my sketch of the original function, or my version of it. And I'm not going to look at this anymore. I'm just going to focus my attention on the arrows and on the concavity here. Let me. Okay, so here's my f of x sketch. I want a relative max at negative 2, so I'm just going to create a situation where there's relative max. So when I create a relative max, I just like to pick a point that is relatively high. At 1, I want neither a max nor min, so I'm just going to place it somewhere in between. And then at 3, I want a relative minimum, so I'm just going to place a point relatively low. And I just want my graph to resemble what the arrows are showing. Okay. I don't know the curvature yet, but I'm just going to at least have my max and min showing. And now, based off of this, I can also develop where my curvatures are. I mean, my points of inflection. So point inflection is at negative 1. I'll highlight that point. At 1, I'll highlight that point. Then at 2, I'll highlight that point. So basically, I want my graph to continually change curvature from red point to red point. So concave down all the way to negative 1. So I'm going to over-exaggerate that curvature. From negative 1 to 1, concave up. 1 to 2, concave down. And then from 2 to 4, concave up. And I think being able to take this information and sketch your own graph will just make matching a little easier. let's do some derivative rules here. This is number 41. Find dy dx, find the derivative. Okay, we talked about how trig functions has an added component with chain rule. So we know we got to involve chain rule here. But before we do that, we want to make it easier to identify the different parts that we want to use. So we're going to first rewrite the problem. Let's get that exponent in a more helpful location, especially if we want to involve derivative process. So we're going to put that 2 outside a set of brackets. Now it's a lot easier to identify the parts that we want to use, right? So now we can identify the outside, the inside, and the inner portion. Outside is my bracket squared. Inside is my cosine parentheses. And my inner portion is my 2x. Okay, find each derivative, bracket squared first, so 2 bracket to the first power. Fill in that space with the original problem. Next up, cosine's derivative. In a separate location, cosine becomes negative sine. Fill in that space with the original inner. And finally, inner's derivative is times 2. Notice that they are all sprawled out, all in a separate location. We don't compact it all into the same space. They're all going to take up their own space, each derivative. Okay, clean up. I'm going to push the coefficients out in front here. So answer choice B. Okay, a couple of small things here. Just want to go through them. Why don't we do a linear approximation problem? I'm just going to create one here. So linear approximation, let's say I had y of 3 is equal to 4, and y prime of 3 is equal to 9. And let's say you want to approximate y of 3.2. So there's 2 things involved, right? Linear approximation, the first thing we do is let's just focus on getting that tangent line equation. %95 of your effort is going to be here. And then once you get that equation, then you can worry about the decimal. So our tangent line equation, all we need is order pair and slope. So it looks like we don't have to go through the process of finding the derivative. But if it was a function, then we find the derivative, find the slope, but everything's already given to us here. So our tangent line equation, we can just put it into our formula, point slope form. Slope is 9. X minus 3. I'm going to do a little bit of cleanup with my tangent line equation just to get that y by itself. So most of the problem is already done. Here's your final step. Put that decimal in for the x and see what value you get. .8. Okay, all right, one more. Let's do a derivative of inverse at a point. So let's say f and g are inverses of each other. Let's say that's established. And let's see. Find g prime of 4. And let's say all this information was given to us. Let's say we're given that g of 4 is equal to 3. We're given that f of 4 is equal to 6. F of 3 is equal to 4. F prime of 4 is equal to 8. F prime of 3 is equal to 2. Okay. Sometimes there may be some distractors where we may not need everything that we see. But I know that f and g are related. I like to create my chart here to help organize my information. In my top space, I'm going to put the fact that their order pairs are going to be flip-flopped, but then below I'm going to show that their slopes are going to be reciprocals. So I know my target is g prime of 4. Really, I'm just going to work my way around this chart, and by the time I return back to it, I will have enough information to know what the slope is. So I know that's the x value of my g function, so I'm looking for g of 4. G of 4 is equal to 3. And if I have order pair 4, 3 on my g function, then what do I have on my f side of things? 3, 4. So we're not going to use this, right? This 4, 6 is not going to be helpful for us. We want to use that 3, 4. And if I have f of 3 equals 4, then I really want to target my slope.
Good morning, Milton Eagles. Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. You may be seated. Please pause for a moment of quiet reflection. This is a time for us to commit to taking the steps necessary to stay healthy during COVID. Before coming to school every day, ask yourself, how am I feeling today? Do I feel like I have a fever or any other symptoms? Let's all commit today to ourselves and each other. To wear our masks, stay social distance, wash our hands directional signage in the hallway. This is a commitment